All right, so the first thing we need to know in this lesson is that there's this new notation. So when you hear the word antiderivative, which I haven't really told you what it is yet, but maybe you can figure it out. This is one of the notations you'll see for an antiderivative. Okay. And we'd say that this is the antiderivative for a function as long as, if we take the derivative, it gets us back to the function we started with. So what we're trying to do today is, we're kind of trying to work backwards. We're trying, instead of to take a derivative, we're trying to say, well, if this is the derivative I'm looking at, what's the function that I started with? Okay, so that's the best way we should think about an antiderivative. Is it's sort of like, you can kind of think it as reversing the derivative process. So maybe an example will help clarify what I mean by trying to go backwards or reverse our thought process. So when you see something like y equals 2, and I ask you for an antiderivative, what I'm saying is, this is the derivative. This here is a derivative. If so, what was the function before I took the derivative? Can anybody figure out how would you go backwards? Oh, good. Okay, well, actually, you're all wrong. It's not 2x. It's 2x plus 2. Could it be anything else?
Yeah, it could be 2x plus pi.
Oh, okay. Creative. Could it be anything else?
Any sort of constant.
Right. So that's the point, is any constant that we had. You were correct, by the way, if you said 2x. I was just being cheeky. So usually when you see your answers written, you'll find this constant here in the answers or your answer key. Because we call this just the general solution, or the solution. We need more information to figure out what constant was there, because the constant was destroyed when we took the derivative, right? We have to find a way to get it back. So here's the notation that we work with. Basically, this is the function that we're given. And this is, we're going to take the antiderivative with respect to, and in this case it would be x. So it's going to make more, in our course we're only going to be doing antiderivatives on one variable, but in other courses, like those of you who are going to be
RT
with respect to. That's a common abbreviation for math anyways, with respect to. But when you get, like those of you who tortured souls that are going to become engineers are going to have to do like three-dimensional calculus and other things like that, and you'll have many variables, and it'll make more sense then why we record this. It'll also make sense when we talk tomorrow just about what is this and what use can we get from it. Right now, like I said, we're just sort of kind of getting a feel for it, and kind of like when we had tangents and we rates of change. First we learned about what a derivative was, and then I told you, oh yeah, by the way, it has all this stuff that it's connected with. So first what I'd like you to do is, if you've got your text with you, if you don't, that's okay. But you may want to refer, just leave it open on your desk. There's a set of generic integration rules on page 278. So maybe I'll bring them up here. I think I have them at the end of these notes, but here's so like this side here, this is what we've already done. This is the differentiation stuff. We've worked through all that. The other side is the differentiation going backwards. So we're basically working on the right side in this unit. Okay? The one that we're going to practice today, I mean, there's a lot of stuff there. Yeah, remember how long it took for us to get through the left side? Well, it's going to take just as long to get through the right side. But this is the one we're going to work on today mostly. Okay, so keep that in mind as we practice. The power rule backwards, since that's the one of the easiest places to start. But you may want to refer to that as we do these questions. I must have been feeling awfully mean when I did this, so we're not going to do that one. That question's, yeah, it's just taking too long. So I'm going to scrap it for now. We don't need to know that level of it just yet. But here's what this is the answer I've given you, but in this section for integration, it's kind of nice because theoretically you can get 100% because you can check all your work real easy. So for example, let's say this was a quiz question. and you wanted to check, have I done this correctly? Is this the function, and is this actually its antiderivative? Well, the way we get back from the antiderivative to the function is to take its derivative. So we can verify it by saying, what would its derivative be? That would be 4x cubed, and then this piece here would have a derivative of minus 1 over x squared, and then the constant would be gone. So yes, it does match back up with the function I started with, therefore it is the antiderivative. So we can check our work in all these ones because we have to be able to go backwards and forwards now. So let's take a look at the integral of x plus 1 with respect to x. So what do you think? Can anybody figure out how could you go backwards from that to the function you started with? Any takers? Sure, Anthony, give it a shot.
X squared over 2 plus x plus the constant.
Yeah, that's right. So the power rule backwards, I'm going to put the power rule backwards for you in our margin here. If I want the integral of x to the n, you got to think about how you go backwards. So in the power rule, tell me one thing you do in the power rule.
Go backward.
Like regular differentiation power rule, what's one thing we do? What about the exponent? Right, and then what happens to it? So we subtract 1, so what are we going to do now? Add 1, okay, so it's going to be 1 higher. And instead of multiplying in the front, how do you think we get rid of that multiplication? Divide, right. So that's how we go backwards fast. So for example, in this one here, how do you get from x to x squared over 2? I mean, fractions aren't always the easiest to work with, but the answer was exponent is 1. To go backwards, I go 1 higher, x squared, divided by 2. So see if you can do it here. Try to work the power rule backwards on the next one. So at some point you're going to feel comfortable, like, you know how fast the power rule goes for you now when you differentiate? You're going to be able to go just as fast when you work backwards, but it obviously takes a little practice. But this is, let me just double check here. Yeah, we're all right. So for example, I've got 4 here, so that means 1 up is 5, divide by 5. From squared, it's cubed, divide by 3. And then from x, it goes squared, divide by 2. Okay. So that is the power rule. I'm going to have us, that's all we're going to practice today is going backwards on the power rule. I shouldn't say that. There's a couple other small things, because obviously you can see a sign there in your notes. But we also want to try, maybe we need to rewrite before we do some of this stuff. That was the first thing we learned in differentiation, right? Was how do we rewrite something and make it easier? So does anyone have a suggestion for how to rewrite 1 over x cubed? Yeah, so just like we did with differentiation, a lot of the techniques are going to be very similar. So what will we do here? What would be the antiderivative of x to the negative 3? Yeah, so the next one up is negative 2. So it'll be x to the negative 2 over negative 2 plus a constant. Like, that's easier to do than try and figure it out all from the start, right? Just use the power rule. And then again, this one here, we'd probably do the same thing. We'd rewrite it at a half. And then at this point, hopefully the fractions are not the issue here for you. So 1 higher would be x to the 3 halves. Divide by 3 halves. Now, dividing by 3 halves, that's the same thing as multiplying by 2/3. So this is most likely the way we'd want our final answer. Now, as you get more comfortable with antiderivatives, you probably won't do this next piece, but while it's brand new to you, get the clutter out of the way so that you can just focus on an antiderivative. So in this example here, this 2 doesn't really do us any harm, but it might kind of confuse what it is you're looking for. In a derivative, the constant has no effect, right? The constant just stays there. Constant times the function will be the derivative of a function times a constant will be the constant times the derivative, right? So we can pull it out just the same when we do the antiderivative. So while you're getting used to this idea, it might be a good idea to separate it, and now I'm only thinking about what's the antiderivative of sine x. Can you do that one yet? What do you think? Good, yeah, it'd be negative cos x. So it'd be 2 times negative cos x plus a constant. So it'd look like this. Now, the next one I'm going to have you try it. You would definitely want to ask your neighbor about this one, I think. But anyway, see what you come up with. It's an interesting one. So let's take a look at the next one. Just out of curiosity, how many people went like this? Maybe you started here, and then maybe you went like this. Can I just see hands up? How many people did that? Oh, a bunch of rookies, eh? No, I'm just kidding. Sometimes you gotta think here, right? Because when you go one higher, where are you gonna be?
0.
Right? Something went wrong. So maybe we should go back and think, before we did this, do you recognize that as a derivative of something? Natural log, yeah. So this would be 3 times the natural log plus a constant. Now one thing here to be careful of, the best answer we would provide in this case, and if you look in your rules, it would be the absolute value, because we can't stick negatives in for the natural log. So I will be fairly lenient about that, but if you notice in the rules in your book, the absolute value sign's there too. Again, it prevents us from putting a negative in the log.
What happens if you do that?
If you put a negative in the log,
Yeah.
it's undefined.
Why is it undefined?
Don't have time in this lesson, unfortunately, but Math 12, that's something we talked about from Math 12 that we can talk about later, okay? So anyway, ask me again, maybe at the end of the lesson we'll have time, okay? Okay, how about this one here? Any ideas on how you would tackle this? Anybody have a strategy they would share, possibly? So sometimes when you're thinking antiderivative, you could ask yourself, well, if I wanted to do a derivative, what would be the easiest way to handle doing the derivative here? Well, how many people would give up and do the quotient rule here? How many people see this and go, yeah, I'd do quotient rule if I had to take its derivative? Okay. Is there another thing we could do where we don't need to do quotient rule? We can do something with that square root x, but I'll show you the suggestion and how you recognize this scenario is what you have here is a monomial, right? When there's only one thing on the bottom, it makes it easy to split this up as x over root x plus 1 over root x. So that way I can rewrite this as the integral x to the 1/2 plus x to the negative 1/2. Just use my exponent laws to go from x to the 1, right? And this is like a half. So subtract them, you end up with a half. In the other case, you have negative a half. So the whole point of doing that is now I don't have to go through working quotient rule backwards, which would be quite a challenge. I can just use the power rule. So to power rule one further, it would be x to the 3/2 over 3/2 plus x to the 1/2 over 1/2. And if I tried to, I guess I could tidy this up better. It would be 2/3 x to the 3/2 plus 2x to the 1/2. Now, for trig stuff, we should also think the same way, right? This is going to be pretty challenging to try and do it as it's been presented, but perhaps we can come up with a clever way to rewrite this. Does anybody feel like maybe they could do something to this that instead of having sine over cos squared, maybe we could get this into some other terms. Well, one thing that I'll do for you, sometimes when it's squared like that, you may want to think about it like this. Can we go a step further? So somebody sees a tangent, so why don't we rewrite that? Is there anything else? Secant. Okay, so why would tangent and secant be advantageous to us? You're correct. But remember, now that we're working backwards, we kind of have to have a goal in mind or we're going to be backing up into nothing, right? Myron, you got something to tell? Well, I'm taking this piece as tangent. So that just leaves this piece as secant. Is that okay? So if you're not, it's our first day, so of course we're not experts yet. But if we look on our chart, does anybody see a rule that might be helpful? Oh, it's the secant's derivative, yeah. So this would be equal to the secant plus a constant. So what we did is we went this way, right? We would have said secant's derivative is tangent x times secant x. Now you're going this way, trying to think backwards, right? So that's what I mean is if you have a goal in mind, like splitting this into two functions, what two functions would make sense? Well, if you look on your rules, there's an integral that has a tangent and a secant. So maybe that's the one we're looking for. Okay. Leave that for now in case people are copying it. So the next thing, I'm going to walk through the first one with you, and then the next one I'll have you try on your own. This is a pretty important idea, and we will spend more time on it. In fact, in your textbook, there's a whole chapter on it. And if you to go on to university, there's probably, I'm sure you could do a PhD studying nothing but this. Anyways, these are what we call differential equations. So it's an equation that's based on a derivative. And if you kind of know a little bit of history, does anybody know what Newton was doing when he figured out kind of how calculus worked?
He was inventing the cat flap?
No.
Because he did invent the
Well,
cat
think about it. What other things is Newton known for?
He was crazy.
Well, other than the apple, what was he doing about the apple?
Eating it.
Gravity, okay. So like, we know him in math for calculus, but what is he really what was Newton really interested in? Like
Alchemy.
Physics and those sciences, right? So he was actually looking at planetary motion, and how the planet's changing, all this motion and stuff. He was looking for a way to describe motion. So this is something that's moving here, right? You have to think, maybe you have a model for something that's moving, right? How would I figure out its position? If I know it's moving, how it's moving, can you figure out a way that I could get its position? The antiderivative, well, I mean, maybe it's obvious because that's the topic, but think about the way we've already talked about this, right? You've got a position, its rate of change gives us the velocity, its rate of change gives us acceleration. Well, now we're developing a set of tools to go backwards, right? Acceleration could take us to velocity, could take us to position. So the problem is we lose that constant at every spot. So if we know something about the original equation, and that's what we know about the original, then we can use that information to find the constant we've missed. Okay, so obviously this is nothing like Newton was looking at, but possibly he found this was the way the planet was moving, and at one point in time he said, now I've recorded a specific position of the planet, and I know how it's moving. So I'm going to use those two things to develop the formula for its position. So to go backwards, this would be x squared plus 3x plus some constant. And then we put in 1 squared plus 3 times 1 plus the constant has to be equal to 3, given the observation that we've made in the real world. Okay? So now, when we look at this, we would say, okay, that's 4 plus the constant is 3, so my constant is -1. Now I have a model, x squared plus 3x minus 1, that tells me all about the position of whatever this thing is that I'm looking at. Now it's not limited to just motion, right? Maybe we're studying a population of animals, right? and we're looking at the change in their population over time. Well, we want to work backwards and know specific populations, like how many, I don't know, maybe we're looking for Canada geese or something, right? Like how many were there 100 years ago? Well, we need to, from the changes we've observed, and maybe we've kind of got an estimate for the current population, that could serve as a model to make this equation that could tell us 100 years ago, or 100 years from now, how many geese we would expect to see. So anyway, try this next one over here on your own, and then we'll see where we're at with these antiderivatives. Okay, so if you're not quite finished, that's okay. Just you can kind of follow along as I check your work against mine, because you know I have been known on the odd occasion to make a small mistake here and there. So here's the antiderivative that I come up with, and I'd like to find the particular solution when f of 2 equals 5. So that's going to be 8 minus 8 plus 4 plus the constant equals 5. So those would be gone. So 4 plus a constant equals 5. My constant must be 1. So the particular solution is going to be x cubed minus 2x squared plus 2x plus 1. Okay, that's the particular equation that solves that scenario. So as I said, we will talk a little bit more about that. It is a topic for AP, but not nearly in any great depth like some of you poor engineers and scientists out there. But the last thing I wanted us to do is then we'll just check and see how you're doing with these techniques. Okay? So here's these questions here, these 4, the last ones we'll do. They all involve, don't do them as they appear, or life is going to be very difficult. Figure out a way to rewrite it so that life's easier. Okay, so I'll do the first 2. I'll show you what I would have. This is how I probably would have chose to do the first one, is to rewrite it in that way. So I'd have 1 higher would be x to the half, and divided by a half, plus a constant. So that's going to be 4 root x plus my constant. Okay, and then in the second example, this one I would probably choose to rewrite it as t to the 4 plus 2t plus 1, because that's way easier to do than think about a chain rule at this point. So it'll be t to the 5 over 5 plus t squared plus t plus some constant. Oh, sorry. Yeah, that should be a squared. So that slightly changes this. It'll be 2t cubed over 3. Is that better? Okay. So I'll let you, in case you haven't finished, I'll give you a couple more minutes to do the last 2. Okay, so this again is that monomial denominator. So I would write this as x cubed over x squared plus 3 over x squared. And then it's going to become x plus 3x to the negative 2. And I'll be able to use my power rule for that. So it's going to be x squared over 2 plus 3x to the negative 1 over negative 1 plus a constant. So I might as well, I could call that x squared over 2 minus 3 over x plus a constant. And in the last one, I'm just going to distribute that. So I'm going to end up with x to the 4 thirds, because there's a 1 here and a 1/3 there. Take away 4x to the 1/3, because that's going to be easier for me to do the power rule on. So working backwards, it's going to be x to the 7 thirds divided by 7 thirds minus 4 x to the 4 thirds over 4 thirds plus a constant. And so after I tidy it up, I should end up with this.